Okay, practice 9.3. Number 1, the Environmental Protection Agency has determined that safe drinking water should contain no more than 1.3 milligrams per liter of copper. You're testing water from a new source and you take 30 water samples. The mean copper content in your sample is 1.36 milligrams per liter and the standard deviation is 0.18 milligrams per liter. There do not appear to be any outliers in your data. A, do these samples provide convincing evidence at the alpha 0.05 or 5% level that the water from the source contains unsafe levels of copper? Justify your answer. So we need to go ahead and do a whole test of significance, and we are going to be working with a t-test because we have a sample standard deviation. We do not have a population standard deviation, okay? So within the state part of our testing, we need to identify the parameters. So we're going to say mu is equal to the mean copper content of drinking water. We need to set up our null hypothesis. So we have the mean is 1.3 because that is what, you know, the cutoff. If it's safe, if it's at 1.3. If it's anything greater than 1.3, then it's actually unsafe. So we want to test to see if we have any unsafe levels. So our null hypothesis is going to be that the mean level of copper is actually greater than 1.3. And don't forget, even though it was stated for us that the alpha is 0.05, within the state part of our process, we do need to identify that the alpha level is 0.05. Then we move to the plan. Remember that the plan is also 4 parts. We need to name the test. We are going to do a t-test. And so we've got to show the conditions that allow us to do a t-test. So we need to say that the sample is going to be random. I said they must pull random samples from different locations in the water source. It really doesn't address the random component. It doesn't say they're doing an SRS or anything like that. But obviously they need to go to different parts of the water source and get different places, like different, you know, locations, you know, some from the middle, some from the edges, so that they're getting it randomly from the water source. And then 10% again is assumed. Kind of have an infinite supply of water because as it rains, you know, it's going to fill it back up and things like that. So it's really assumed that these 30 samples is going to be less than or equal to 1/10 of all the water in the world. And then the large sample this time is actually met because you're taking 30 samples. So n is greater than or equal to 30. So we could stop right there. They did interestingly point out that there aren't any outliers, which is interesting because if it was less than 30, then that would be important because we would have to look at the graph and they don't give us data to graph. So we would have to rely on the fact that there aren't any outliers, which would cause it to not have a strong skewness. Okay, on do, I'm just going to use my calculator. So I'm going into stat, over to test, and with means, we're doing a t-test. So that's number 2. We have data. We don't have data, excuse me. If we had data, we'd put it in a list and we'd run it that way, but we actually have statistics. So we come on down and we change that to stats. Okay, so then we have this information. The mu naught is going to be the hypothesized or the claimed value. So it's going to be the 1.3. Just remember that it's always the number that you're using when you write up your hypothesis. The x bar is their sample mean. So when they actually took the sample of 30 different water samples, they got a mean of 1.36. So that's going to be our x bar. And then Sx is your sample standard deviation. So from the sample of 30, they got 0.18 for their sample standard deviation. Okay, the sample size they used was 30, and then we're testing to see if the water is unsafe. So we're looking for where the copper level is above the 1.3. So we're going to select greater than, and notice that I did write all of these things that I have in the calculator. I do want to put those in the do portion of my write-up. And then I go ahead and go down here to calculate, and for the output, you want to make sure you put the test statistic and the p-value. And notice I added one more little extra thing in there. They're going to want to see that you know that since you're doing the test statistic that you have to know the degrees of freedom as well. Because if we were truly looking this up on a table, then we would have to also know not only the test statistic, but we would have to know the degrees of freedom as well. So I went ahead and added that also. Since we have a sample size of 30, we know that the degree of freedom is always one less than our sample size. So that gives us a DF, which is degrees of freedom, of 29. And then the t is the test statistic we get from the calculator. Rounded is about 1.83. And then the p-value, again, from the calculator is 0.039. The other bits of information, the x bar, sx, and n, I don't need to write that down again because I've already put it as the initial things that I had put in, okay? So based on the p-value that we got a p-value of 0.039. That is less than alpha. So I'm working on my conclusion now. So since 0.039 is less than alpha, p is less than alpha, we reject the null hypothesis. It's not enough to give the statistical conclusion. You do need to say reject the null, but then you need to go on and say, what does that mean in the context of this problem? If we're rejecting the null, we're saying this is probably not true, this is probably true, then we're going to say there's convincing evidence for the alternative hypothesis. So there is convincing evidence that the mean copper content is more than 1.3. So we do have convincing evidence that the water that we've found in this new source is actually unsafe. So it is, the data that we got is significant enough to say that the water is unsafe. Okay, how would your conclusion change if your sample mean had been 1.355 milligrams per liter? What point does this make about statistical significance? So what I did is I just went in and changed that number. Like, we have such an amazing tool in our calculator that if they want the sample mean, instead of being 1.36 that it was before, and they're like, okay, no, change it to 1.355, I can just go rerun it. Because we have this tool that allows us to do it very quickly. So the hypothesized mean would still be the 1.3. They're changing the x bar to 1.355. We're going to leave the standard deviation, leave the sample size, leave the sign for our alternative hypothesis being greater than, and we're just going to rerun it and see what would have happened. So if we recalculated it with that different mean, notice that now we have a p-value of 0.05. So with that little bit of a difference of a sample mean, it actually causes us to completely change our conclusion. On the last one, we had p was less than alpha, so we rejected. So now with that little bitty change to our sample mean, now we fail to reject the completely opposite conclusion. So what should we have seen is that a very small change to the sample mean can completely change your conclusion. So even just a little bitty alteration can really make a big difference statistically speaking. Okay, number 2, a consumer advocacy group tests the mean vitamin C content of 50 different brands of bottled juices using, in each case, a t-test of significance, and with the null hypothesis is the mean amount of vitamin C that is on the nutrition facts label for that brand of juice. They find that 2 of the 50 juice brands have statistically significantly lower vitamin C than claimed at the alpha is 0.05 level. Is this an important discovery, and explain? So basically they're asking, is it a big deal that 2 out of the 50 basically don't have enough vitamin C? That's kind of how I'm reading it. They find that 2 of the 50 have lower vitamin C. So remember that your significance level is the probability of making a type 1 error. So since they set the significance level to be 0.05, that means we have a 5% probability of basically being wrong. So 5% of the time you would reject the null when you really shouldn't have. So we have 5% of 50 because they're doing a sample of 50. So if you look at 5% of 50, we should see that that's 2.5. Like if you do 0.05 times 50. Hopefully y'all believe me, but I'll show it really quick. 0.05 times 50. Is 2.5. So it's almost like you have a room for error of 2.5. So you only found 2 out of the 50. So it's not really that significant because we could have gone as much as 2.5 of them not having enough calcium or vitamin C, excuse me. 2.5 of these bottles of juice could have not had enough vitamin C, and our tests still be okay because of that little room for error that we have there. So we would go on to say it's not very significant, so it's not an important discovery. Now, if they would have found 3 out of 50 or 4 out of 50 or 5 out of 50 or so on, then we would say it's significant enough that there's been a mistake made. But that 5% times 50 allows us a 2.5 kind of cushion that as long as it's within that amount, then we're okay with the testing, the conclusion that we've come up with. Okay. Number 3, Tai Chi is often recommended as a way to improve balance and flexibility in the elderly. Below are before and after flexibility ratings on a 1 to 10 scale, 10 being the most flexible, for 8 men in their 80s who took Tai Chi lessons for 6 months. Do these paired data adequately meet the normality condition for a T procedure? Justify your answer. I really wish they would have asked you to actually carry out this T test. So I'm going to do that, even though you don't really have to, just to show you kind of how you would do it on the calculator. When it comes test time, you may have to actually work out a T test given data like this. So anyway, we have the flexibility rating after Tai Chi, and you want it to be higher than their flexibility rating before Tai Chi, because we're hoping that they're going to get more limber and everything after they've gone through this program. And so the numbers that I came up with at the bottom is going to be their flexibility rating after minus their flexibility rating before. So you do 2 minus 1, you get the 1, and then 4 minus 2, you get the 2, 3 minus 1, you get the 2, 3 minus 2, you get the 1, and so on. 3 minus 1, 4 minus 4, 5 minus 2, and then 10 minus 6. And so we need just to answer their question, this is one of our conditions, to meet the normality condition, we need to look at the distribution and see if we have strong skewness or if we have any outliers, because we don't have a big enough sample size. Our sample size is only 8. We have 8 different sets of data points, and we need n to be greater than or equal to 30 in order to assume a normal distribution or be able to do the T test, the T procedure as they're calling it. So we don't have the 30, and so we can do a dot plot, we can put the data in our calculator, look at a box plot, but either way, I went ahead and did a dot plot up here just because that's how they did it on the answer key. I did 0 through 4 because those were the different differences we had. We had 1 0, we had 2 1s, we had it looks like 3 2s, and then just 1 3 and 1 4. So that's how I decided how many dots, obviously, to put over each of the numbers. And you can see it doesn't look very skewed. It may, possibly you could argue skewed to the right a little bit, but no, it's not really super skewed or anything like that. The other place, like I said, you can look at it is in the calculator. So I'm going to do that really quick. So I'm going to do stat edit. I'm going to put just the differences in the calculator. So 1 2 2. 1 2 0 3 and 4. Hopefully I got them. So then I'm going to do second y equals, because I want to go do the box plot. And so I'm going to turn it on, and I'm going to come down here to the type, and I'm going to change it to the box plot that has outliers, because I want to see them if there are any. And I'm going to do zoom 9. Okay, and so you can see there's no dots hanging out on the end of there. You do see that it looks a tiny bit skewed to the right, but it's not a strong skewness. So that is what allows us to carry out with the testing. So if you actually had to do the test, the way you would write up your hypotheses is you would say the null hypothesis would be that the mean difference is just equal to 0, and then the alternative would be that the mean difference is greater than 0, because you want them to get better for when they're doing the Tai Chi. And I guess the way I subtracted it, let's see, we would probably actually want to do less than. Let's see, rating after and then rating before. After minus before greater than 0. Yeah, we want it to be greater than 0 because you want your after to be higher than your before. So anyway, go on over to test. Sorry about that. Number 2 for the T test, we have data this time, and I have it entered. So I'm going to go for the input. I'm going to select data. I'm going to change my mu naught to 0. If there was no, if Tai Chi didn't make a difference in my flexibility, then there would be no difference in my after and my before. So that would be 0. My data's in list 1. I'm hoping that I got the sign right, guys. So I'm going to do greater than, and I'm going to go down to calculate. Okay, and so I have a really low p-value at 0.00. It looks like 19 maybe, 0.002. And so p is definitely less than alpha, and so we would reject the null. And so we do have convincing evidence that Tai Chi is actually increasing their flexibility. It does look like they're doing better if they've had the Tai Chi in their flexibility. So we have some statistical evidence to support the claim that the Tai Chi is making them more flexible. Okay. And again, you didn't have to do all that. You won't have to do that on the daily check. You're just going to have to show on the daily check that show the graphed distribution of their differences, and then say that there's no strong skewness and no outliers. And then your favorite question, if it's not your favorite question, I don't know, how to make it your favorite. It's so easy. Just memorize, how do you increase the power? They give you this whole long scenario, but essentially their question is, what 2 ways can you increase the power? And I just want you to memorize, increase the sample size, increase the significance level. That is what we have to know about increasing the power. How do you do it? You increase the sample size and you increase the significance level.